Welcome. This is a rather special talk on EMG in myopathy. We will discuss some things that are not used or thought of in routine. We record the motor unit, which is indicated here as a round structure, which is not the true thing. It is a 5 to 15 millimeters in a rough diameter. We record the activity with different magnification, if you wish, from small single fiber EMG, a few hundred micron, to a few millimeters with concentric and monopolar electrode, to a larger uptake area with a cannula recording called macro EMG, and with the superficial 1 or 2 centimeter layer of muscle by means of surface electrode. Now we are going to use an EMG simulator for understanding of the relationship between the EMG signal and the generator, the muscle fiber that is. Here is the cross section of the muscle, longitudinal section of the muscle with motor end plates here, and an area where we can insert muscle fibers, which I do now. Here are 100 muscle fibers inserted randomly, and here is a needle electrode that I can move around like this. Here we have the muscle fibers in a normal motor unit generating this particular motor unit potential. And now the question is muscle fiber dropout the reason for polyphasicity, the early sign in myopathy? I am going to delete one fiber after the other, and you watch here if the signal is getting more and more complex. I will remove that fiber. I remove this fiber. I remove this fiber. I remove this fiber, and I remove this fiber, and you see that the signal is not getting more complex, rather more simple, and with shorter duration. So we must test something else. We are going therefore to insert. Here we have here we have the motor unit potential again, and now we are going to change the fiber diameters from 50 plus minus 5 to 45 plus minus 15. That means some large muscle fibers, some thin muscle fibers. Conduction velocity along muscle fibers is related to the fiber diameter. And here I make the change, and you see immediately that we get extra phases. So it is very easy to produce these extra phases just by changing fiber diameters. And this is particularly obvious when we record at some distance from the motor end plate zone. And that is because we have an increased temporal dispersion. There is a greater difference in arrival time between the fast action potentials and the slow action potentials, and the other way around, that when we have shorter distance, we're closer to the end plate, then we get very homogeneous normal looking motor unit potentials. This may be one of the reasons why in myopathy we have both normal motor unit potentials and so-called abnormal motor unit potentials. It is important from this little experiment that we use a standardized position for the recording, similar to the one we have used when collecting reference material. So then we go back to the figures here and make a summary explanation of the motor unit potentials of myopathy. The lesson we just learned is that polyphasicity reflects fiber diameter variation, which we see in muscle biopsies. Polyphasicity is more pronounced away from the end plate, and loss of fibers do not give a polyphasicity, but only reduction in duration and amplitude. And now we can go the other way around. Is it possible to see these biopsy changes in the EMG, and which parameter should we look for? Well, muscle fiber diameter variation, can we see that? Loss of muscle fibers, the distribution of muscle fibers in the motor unit, muscle hypertrophy and hyperexcitability. Let's take one after the other here. First of all, muscle fiber diameter variation. We have polyphasic motor unit potentials in myopathy. Some look normal, but some are very polyphasic, and the polyphasic ones are sometimes very long because of the slow conduction of the thinnest muscle fibers. So here is one recording of 20 in one muscle. Here's another recording of one motor unit in a Duchenne boy. It starts here with trigger, and here's the end of the signal, which is 50 milliseconds later. So if the firing rate is 20 Hertz, then the motor unit potential starts again just before it has ended. And if the firing rate is higher than 20 Hertz in this particular case, then the motor unit may start its activity already before the previous motor unit potential has ended. Quite a confusing situation. So that was the indication of fiber diameter variation. And then the next parameter, can we see loss of muscle fibers? Well, we have low amplitude of the motor unit potentials in a conventional EMG. We see the low macro amplitude. Macro is recording from the cannula, a non-selective recording. And we have loss of muscle fibers, which is not evenly distributed across the motor unit, but it can be focal loss of fibers, patchy loss of fibers, as we see in a special EMG technique. Here are some examples. This is concentric motor unit potentials, a few of them in a normal muscle, and the smallness of the motor unit potential and the complexity in some of them in certain areas. The macro EMG can easily see the size of the motor unit. Here is the 20 normal macro EMG signals with a certain amplitude, and here is the smallness seen in a patient with myopathy. The next parameter that we wanted to investigate is the distribution of muscle fibers within the motor unit and the patchy loss of fibers. We have a special technique by which we pull a concentric needle electrode, for example, through the motor unit in 50 micron steps. So it's quite a lot of steps here. And we trigger with a separate needle electrode in constant position to make sure that all these action potentials come from the same motor unit. And you see how a given motor unit really changes its shape as we go to different parts of the motor unit. If we happen to do an ordinary EMG, we go in either here, or we go in here, or we go in here, only one of the traces. This is a normal muscle. If we look at a muscle from a patient with muscular dystrophy, we see areas that have very polyphasic motor unit potentials here. Either other areas with short duration potentials, and the most important, there are empty areas where we have no muscle fibers at all. And we can look at the amplitude profile here, and we see how it goes down at some areas. And we have looked at this statistically, and it's quite a true fact. Then another thing is muscle fiber splitting. We sometimes in biopsies from patients with myopathy, we see a slight tendency to grouping, and the explanation for this may be muscle fiber splitting. That means that a muscle fiber has a longitudinal split, and it can create 2 branches, 5 branches, even 10 branches. And here is the same recording as we saw previously. A small group of signals here, and maybe 3 spikes, and they don't show a jitter at all. That means that they have the same motor template. That means that it must come from 3 branches of a split muscle fiber. And more convincing maybe is that we here record with a single fiber needle electrode, trigger on one spike, and look at the jitter of the other spike, and there's no jitter at all. Well, less than 5 microseconds, which is the noise in the system. So when we have no jitter, it means that the 2 spikes here are coming from generators with the same motor template. And this must be a split fiber. This is more often seen in the myopathy than we tend to see in the biopsy. We can measure the fiber type grouping, namely the tendency of fibers to be clustered, and it's typically seen in reinnervation. And here's the principle that we go close to one fiber and see how many fibers are there from the same motor unit synchronously firing within the uptake area, and usually it's only 1 or 2. But if we have reinnervation or clustering of muscle fibers, then we have more fibers from the same motor unit in a given small area. And now we have looked at fiber density in myopathy, and here is the finding from a few patients. This is the normal value of fiber density in extensor digitorum and biceps in Duchenne, muscular dystrophy, limb girdle, and so on. And here you see how the fiber density is distinctly increased in Duchenne boy, and also very much increased in unspecified limb girdle types of myopathy, and actually in all of them. And how is it possible that we see increased fiber density? Well, one possibility is that we are actually recording in this area where the electrode can pick up activity from different branches of a longitudinal split. Here we may see 3 action potentials that are very close together and do not show any jitter. There are other possibilities for increased fiber density also that we don't go into here. Michael Swash and colleagues long ago made a special study of the splitting phenomenon. They made slices of a muscle fiber with short intervals, about 200 micron, over a long distance of muscle fibers in both in polymyositis and in some neurogenic situations. And they could see that the muscle fiber often showed a splitting phenomenon. It started often where it was a central nucleus, and you could see a small little split. If they were cutting a little further down, they could see that this must be parts of the same muscle fiber, and if they were cutting even further down, then the two branches looked like separate muscle fibers. And here is that you have this central nuclei in a patient with muscular myotonic dystrophy, and here around this area you can see the split in this muscle fiber, just by chance that we happen to have a cut in the muscle that gave us this chance. Maybe in other situations we see more muscle fibers that are cut little further away from the split. So here you can imagine that this must be earlier the same fiber. This is at ATPA staining, so all of these are type 1 muscle fiber, and here we have type 2 muscle fibers, and there is a split here. The whole principle is that both branches here must be either type 1 or type 2. It cannot, here is only one of the types, and here is only one of the types. And then if we cut a little further down, maybe these three has been the same fiber. But we don't know that. We cannot see that in the biopsy because we are away from the splitting process. But electrophysiologically we can see it because there is no jitter in the recording between these three. And here this cannot be a split, for example, between this and this, or this and this, because they have a different staining, so they must belong to different motor units. They are different types. And then we have another phenomenon that we see in our daily routine relatively often in some myopathies, and that is high amplitude short duration motor unit potentials. As you know, the neurogenic are high amplitude long duration, and this has led to misinterpretation in some situations, even in publications. Here is a recording from patient with hereditary distal myopathy with small motor unit potentials, polyphasic motor unit potentials, some that look normal, and all of a sudden some individual recording with very high short duration motor unit potentials. And they are probably generated from hypertrophic muscle fibers. Large fibers give rise to higher amplitudes, but theoretically not yet proven is the possibility that we are recording from a few branches of the same muscle fiber when they are still absolutely synchronized, and they don't show any jitter, so we cannot detect that they are coming from two fibers, but summate to a nice action potential. So these were the findings about fiber diameter change on individual level, but here is on the whole muscle level. When we have patients with proximal myopathy, we often see larger distal muscles, and if we have a distal myopathy we may see a very strong biceps, for example. And here's an example where we measure the size of the motor unit by means of macro EMG over 9 years. It goes from here, and you see over the years motor unit becomes smaller and smaller, and in the distal muscle, and in the proximal muscle with the open symbol the amplitude increases at least to double, and the fiber density does not change much at all. So it's not a case of re-innervation, but fiber or muscle hypertrophy, the whole muscle. Then some discussion about muscle fiber hyperexcitability, ion channel changes or other changes. One is the CRD, complex repetitive discharge, and that is a group of muscle fibers, 5-10 muscle fibers that are activated absolutely synchronously. It starts abruptly, ends abruptly, and is a very typical sign. Electrophysiologically, but it is not a diagnostic label. We cannot tell from which patient this is coming. We see this both in neurogenic conditions and in myogenic. Here is the sound of it. Sometimes it changes in sound because there is a dropout of some of the components. And then it stops abruptly like this. And the explanation may be the following. We have abnormal muscle fibers that are hyperexcitable. We have a fibrillation potential that starts and goes this way and can, with hepatic transmission, activate a neighboring muscle fiber, and we can have a loop here. If it is short, we have a high frequency CRD. If it is long loop, we have a low frequency CRD, and this can also activate the next and the next and the next muscle fiber. And if we have an electrophysiological fatigue somewhere, we may have a group of fibers that drop out later, that we heard in this example. So this was CRD. Another typical hyperexcitability phenomenon is what we see in myotonia. And myotonic discharges explained sometimes as dye bombers with increasing, decreasing amplitude and frequency. That is certainly typical, but often when we insert the needle, we just see positive waves, irregularly firing, and only when we move the needle a little, we see the typical dye bomber. So here we insert the needle, and we have these positive waves. I move the needle. You heard something there, and that is a myotonic run. It is very difficult or impossible to measure the parameters of the motor unit potential in this situation. It's so disturbing with all the spontaneous activity. And one trick is to activate the muscle for a minute before the study. By activation, we can fatigue the muscle fibers in some of the myotonic conditions at least. That is corresponding to the warm-up effect. And then we can make voluntary motor unit potential analysis. Here is the situation in this muscle. Now we ask the patient to activate, and directly after that we look at the activity. And here you see I move the needle to try to provoke myotonia, but it was not possible. So this is the warm-up effect. So these were some of the features I wanted to tell about today. This may not be useful at all in clinical routine electrophysiology, but it may be interesting to know, and it shows the intriguing possibilities we have with recording in different ways from different types of pathology.